Oh, what's up, everybody? Welcome back. Today we are working on our virtualized graphics card, and today's topic is trying to get GPU shaders to execute with runtime data. So, for context, we are implementing a virtualized GPU. What is a virtualized GPU? Well, in the same way that you run a virtual machine and the virtual machine can emulate a CPU, we want to do the same thing with the GPU. Now, these things exist, but we want to make our own so that we can understand the entire graphics stack on Linux to try to get a feel for what a GPU really does, right? The idea being that if we implemented a working GPU completely virtually, then we'll have the tools to design a GPU for real on an FPGA or something. And that's kind of like the end goal here. And what we have right now is we have like QEMU is like an open source virtual machine that runs on Linux. I'm sure it probably runs on Windows as well, but whatever. It's a virtual machine. We can extend this QEMU with our own little PCI card, right? So we have like a PCI device that, when you boot a virtual machine, is seen by the guest as like a real PCI device. This PCI device has like the ability to draw onto the QEMU screen, right? By basically like putting pixels in a pixel grid somewhere and like asking QEMU to draw it. We have written a driver for this thing that lives in the Linux kernel, and he talks to this thing. So he's got driver here. He talks to the PCI card basically by sending commands to like memory mapped regions, I guess you could call it. So like you say, hey, I'd like to write. The PCI card says, hey, I want to expose like 64 bytes of address of like writable space. The BIOS, I believe, in QEMU will like ask the PCI card like, hey, you got anywhere you want to write? And he's like, yes, please. And we're like, okay, here's an address where you can write those things. The BIOS tells that to the kernel driver. The kernel driver then can like just write those addresses, and it will like perform actions on the PCI card. So one of the things that we might be able to do is we might be able to say like clear, right? And that will ask the PCI card to clear the screen with a certain color. We have written a kind of, we're working on, I guess, a user space driver for this thing. So why do we need a user space and a kernel space driver? Because GPUs are complex beasts, and trying to do all of the work that you would need to do to make a GPU work in the kernel is like silly. It's like expensive because working in kernel space requires like context switches, as well as like you have no dependencies and you have to write in C. There's like all sorts of like downsides to doing things that way. So what happens is they expose this like DRM interface, where you can, like, as a GPU driver writer, expose your own commands. So like Sphero clear, right? This Sphero clear is something that we can call from like our mesa driver. And he will basically know how to construct this clear command that our PCI device wants and how to send it over there and how to do the work. We are in the process of writing shaders. So in our little test application, I think it's test app like this, we have like the world's simplest OpenGL pipeline. So in OpenGL, when you want to draw stuff to the screen, you basically upload a set of vertices. Maybe we'll open Blender as an example here. So if you want to like draw this cube, you upload the positions of each of these 8 vertices for this cube, right? And you then ask the GPU to, or you ask OpenGL, I guess, to run this thing called like through a vertex shader. So he'll go through for every point. He'll like split these up into triangles, kind of. He'll like kind of run an action on every point. So if say you want to like scale the cube, right? Every single point you can like multiply by 0.5, and that will make it smaller, right? Because all of these points will get closer to 0. Then you could do something if you like want to move to the side. You ask your shader to say move everything to the left a little bit, right? You have to create a program in OpenGL land, kind of hand wavy. But this program could be dumb as bricks. And so that's what we've done. Our initial test here is like literally just do nothing. Take in a 3D point and output that same 3D point. There's like a little bit of, you need to be a 4-dimensional point when you come out. The 4th dimension is kind of just this like, it's not really a new dimension. It's just like a mathematical construct that makes things easier to manage, called, you can look up homogeneous coordinates if you want to look at that more, but we're going to skip over that for now. Then we have like a fragment shader that runs that basically says for each pixel of a face that's shown on the screen, how do I choose what color that thing is? And we're doing a dumb as bricks one again, where we're just saying like, make it white. The goal is to make our program that uses the shader pipeline work correctly. And we've gotten somewhat close there. We have, in the past couple streams, implemented shader compilation for the vertex shader, to the point where it doesn't crash. So let's see if we can find this in Mesa. I guess we run it. So we can look at like our test app, dev DRI card 1 with ner debug is equal to print vs. Okay. So we get in from that GLSL I just showed you that just basically is like basically nothing. He compiles this like intermediate representation in Mesa land. He does all the heavy lifting for us, and we get this like simple program here. Dereference a var, load the var, load a constant, and like basically combine the constant of 1.0 with the vector that was passed in and store that back in the output. We have converted that into like this like JSON blob that says like basically it's like a set of commands that we know how to execute on our GPU. And we've like proven that if we execute this chunk of JSON, that it will do the expected behavior, right? We've basically made like an interpreter for the Mesa intermediate representation and then dumped out the state of that thing to JSON because we're too lazy to write a binary format right now. That's like the current state. Now, what we have done for kind of like proof of concept here is we've made this call libgpu execute shader. And what that does is if we go into our libgpu implementation, he basically like hard codes an input, some inputs here. He says like, please run this shader with the input of vec3 1 2 3. And what is the output here? And we can like see that we get the output 1 2 3 1, which means that we are correctly loading the constant 1, appending it to our vector. Bing bang boom, everybody's happy, right? Now the goal for today is going to be to try to like hook this up to kind of like a more generic system. So what this is actually supposed to do is we're not supposed to feed it one vector here. We're supposed to feed it like a bunch of vectors, right? The typical flow is like you might have like an object with tons and tons of vertices, right? So we have an example somewhere of like, this is like the Blender monkey, right? You see like there's tons and tons and tons of vertices in here. And so we should be able to run our program on every set of like every chunk of vertices here. Each group of 3 should be turned into a vec3 and be passed into our input, run, and we should get all the outputs. That's what I want to look at today. So we're going to start by trying to figure out how like in OpenGL, this call is done by bind buffer data or something. Let's see if we can find it. GPU. Probably want to go to the test app. So we, for our simple test, are trying to upload basically one triangle. And we call GL buffer data to put that stuff somewhere. And then we like bind that buffer data somewhere and like set his like parameters. So we say, oh, this is like a 3-element vector, I guess we'll call it. They're grouped in 3s. They are floating point and they are this far apart. And we like feed that into OpenGL somehow. We don't really know what happens there. And then when we call draw arrays, he like uses the data we passed in as his input. So we're going to start trying to figure out how to like get that data somewhere that the GPU can access it. Maybe we'll start by just stashing that data in Mesa, and then we'll kind of like work with the GPU side later. Then we are going to try to like actually run the shader like later. So usually like we're running it on like the end of shader compilation right now. We have to like put that thing somewhere, run it on draw with the correct data. Once we have that, then we can kind of figure out how to like integrate with like the GPU itself. So right now we're not doing any upload of shader or buffer data to the GPU. We are just kind of keeping it in Mesa user space for now. And then we'll actually run the execution on the other side. And then we'll draw something on the screen. And if we get through all that, then we can work on fragment shaders. We can keep going. But, you know, for now, we are where we are. So let's get into it. Let's get moving. So I think what we have right now is, let's close this. If we run our application, test app dev DRI card 1, there's supposed to be a triangle on the screen. but instead we just get like a green background. This is supposed to be happening, but there's supposed to be a triangle somewhere as well. We have kind of stubbed out all of the implementations of functions in Mesa that need to be implemented for this to not crash, right? So we can kind of have a clue by which functions we needed to implement to not crash of where the data is supposed to come in. And is this already open? Not here, not here, not here. Oh, I think I opened it here. There we go. Okay. So we can look at our set of functions, and it was kind of like these ones, right? So create shader state, create shader, buffer subdata. This is the one that looks a lot like the GL call that goes with it, GL bind data or GL buffer subdata. Those are both commands that you might use. So we can look in here and see, oh, we have actually, in fact, double check that this data is what we expect to see. So we say data if interpreted as floats is this stuff. And if we look here, we see data if interpreted as floats is what is negative 0.5, negative 0.50, 0.5, negative 0.50, and 0.50, which matches what we passed in from our test app. Source main, right? This vertices. This is in fact the same data. So that's really good for us, really big for us. Which means that we just need to like put that data somewhere for now. Sorry. Okay, so I guess for now, let's think about what this is supposed to do. So this is supposed to create a GPU resource. Maybe? No, he already has the GPU resource. He's supposed to put the data in the GPU resource. Now, I suspect that our pipe resource that we can create here, I remember only implementing this for textures. So we should double check that when somebody tries to create the vertex buffer that we're doing the right thing. And we can tell that we're not. We're unconditionally creating a texture. So we should look at what comes in here. So, like, what is pipe format here? None, R64. Okay. Let's maybe check if we actually get a resource creation request for this thing. That probably makes sense. So can we say like, this is called on resource create. Can we maybe breakpoint here and just kind of see what paths this is getting called on? That might be interesting to us. So we can call like gdb test app dev, gdb args test app dev dri card1. And can we break on sphero drm winsys c line 393? And yes, I'm okay with that happening when you finally load my library because it needs to do some sort of like dynamic loading of my driver. We'll hit run and we'll just kind of see where this is called. Well, we can presume that one of these is for like texture allocation for the like output render buffer. So DRI create image, that's fine. We're not really worried about this one. Resource create here. Okay, so we're on buffer objects here, buffer data, right? So we can actually see here that this is coming from Mesa buffer data, which is GL buffer data, which is making it all the way down here. So this is probably the vertex buffer creation. And can we like poke? Like, what is in this thing? So they're saying that we want something that has an 8-bit unnormalized pipe format R8 unorm. Target pipe buffer sounds very promising. Very promising. Can we look at like maybe who's calling us? We're being called by buffer obj data at bufferobj.c. 352. So he's calling here. These are the parameters that we care about. Want typeless or similar. Okay. Pipe buffer. Okay. So this is probably what we're looking at for now. And here he sets width, height, depth, and size. So here we're basically looking at the width flag. Essentially. Everything else I don't really care about for now. So let's look at the width and here. Okay, so we'll say for now, I think that we want to like not pass anything to the GPU right now. So we're gonna say like if template. What was it? It was the target is just like a raw buffer. I'm assuming that the other ones are textures, right? That's a big assumption, but we'll try it for now. We'll say that if it's pipe buffer, instead of creating a like GPU resource, we'll just kind of create a like Sphero dummy resource. So this is something that's not going to go to the GPU yet. It will eventually, but for now, I don't want to do it that way. So instead, we'll just put the data here. Yeah. And we are just going to be like, we're going to create a dummy resource here. Right. And then we're just going to basically malloc the size. So can we just do like template width? Oh, like this? And then ret PR is equal to template. Okay, return. We return the thing. Okay, so now we know that when we call bind, what is it? Buffer subdata. We should have the input here as our struct. So we should be like Sphero dummy resource is equal to how do we do this before? Are we just casting because of the first element? I think we are. So we should be able to do this. Then we should be able to be like res data. We want to like mem copy this stuff, I guess. From data, size of size. And here we should probably like check for bounds check and etc. But you know, whatever. We're just not going to be wrong for now. Which means that on the draw call, presumably we have this data somewhere. Now, I don't really know if we get the resource in on the draw call. Does the draw info have the resource? Okay. This looks promising. So how do we know if we are in a, if we're like drawing elements? Like how does this index work? If has user indices, use index user, else use index resource. So we're assuming here that like has user indices is false. Then we should be able to go like info resource, index resource. This should be we should be able to cast this to a Sphero dummy resource. We should be able to do that. And here we should see that we can go like that same for loop that we did over here where we printed this stuff as floats. We should actually be able to move that down here. And we should just be able to go through like this. So the size is in width 0. This isn't uploading more. This is like have vertex data of size this. And we should see the same thing. That would be pretty cool. That would be very cool. So let's turn on networking in the VM so that we can upload the latest and greatest versions of our library. And then let's call run a build, upload the stuff, and see what comes out. Give him a sec. He's thinking. Segmentation fault. So not good for us. It looks like that means we don't understand what the fuck is going on. So can we like GDB this thing and just see where the fuck we fucked up? Where did we go wrong? It's in draw VBO 362. So it's here. So this is wrong. Interesting. So we are incorrect here. Can we like print out the value of this thing? So this index, can we like printf? Maybe we can even just like, we can probably do it without recompiling if we get a little clever. We can do dprintf at sphero drm winsys.c line 359. Pointer will say that this is like using this pointer, which is going to come from info index resource, okay? Then when we allocate this thing, which was resource create, here we're going to do a breakpoint here, which is at 409. And we're going to say allocated this thing. And this is going to be red, I guess. Okay, run again. No source file named sphero drm winsys. You'll get there eventually. Okay. So do we have our print? No. Ugh. That's annoying. That's annoying. I guess we'll just do it the old way, the old-fashioned way. So break sphero drm winsys.c 409. Sphero drm winsys. Where was the other place? 359. Okay, give him a sec. So this is the buffer opt one. Hell yeah. Okay, so can we print out the red? Okay. It's hard to read that, but that is 2BCO. And then can we look at p info resource index? That was it. It was resource. That's 4003. So that's not the same thing at all, which means that this is the wrong spot. Can we look at the index size? It says that's supposed to be 0 if it's not indexed. Okay, great. Then, like, why is this resource fucked? If has user indices. False. Okay. So that makes sense. We are supposed to use index resource. Can we look at like with 0 here? It's like saying that that's invalid memory, which makes sense. So who's calling us here? This is u vbuff draw vbo. Kind of over here, which kind of gets his stuff from up above. So CSO draw VBO. Okay, so this is here. So he also has the draw info coming from above. ST draw gallium. Also comes from above, right? Draw info. So that's going to come from like here somewhere, info. Okay, so we're in like mesa draw arrays. Here we go. So info. He never sets that thing. Where does like the data come from then? Unless draw gallium modifies it. I missed that. What was it called? It was st draw gallium. So he just kind of passes through. This guy also just passes through, which passes through to vbuff draw vbo. Kind of like here somewhere. And then does he set like the index? Okay, so he does a lot of stuff in here. So does he set like... Okay, wait, hold on. Okay. So he does use index.resource a little bit. But it kind of also looks like up in some cases he expects that to already exist. Where does the data come from? Where does the data come from? Get the number of draws. You read the use buffer range only once. End vertex, start vertex, new draw, start instance, end vertex, end instance. What's your advice to learn new programming things eventually become better? I think just practice. I think it's the same as everything. You just gotta like do the reps and make sure that you're doing your best to like practice intelligently, right? Like make sure that you're trying to understand what's going on, and over time you'll have more stuff in your tool belt and you'll be able to do it more. I don't know. It's about the extent of what I can give you, man. Just try stuff. At least that's my approach. But also, who knows if my approach is the same as everybody else's? What works for me might not work for you. So you gotta try stuff to figure out what works. This is at 1499. So we're in this path, which means that kind of like nothing is getting modified, which makes me think maybe this info is not where we're supposed to be looking. Maybe not. Read books. I'm not really much of a book reader, but if reading books works for you, then you should read books. This does not have any data in it. Does this have data in it? Oh, buffer. Here we go. This looks like what I'm looking for. So draw indirect info. What the fuck is this thing? Indirect draw parameters resource is laid below. I don't think we're doing an indirect draw though. I don't think. I guess we could look in the debugger and see if anything looks sane here. Can we look at like indirect is null? Draws has some stuff, but this doesn't really seem that interesting. Start count and index bias. Sure, I don't really care about that. Which really makes it seem like this is where the data is supposed to be in this draw info. It really feels like it's supposed to be in here. But again, if we look at like info, both like index and resource, like they don't really seem like correct. They're like unaligned pointers. So I guess maybe we're missing some sort of like bind call or something. It could be if it's like stateful. So we have like bind vertex shader state, which I think is kind of more about the I think this is more about, how do I say this? Like the compiled vertex shader. Set vertex buffers sounds maybe interesting. What's going on in here? This feels like maybe important. uh Seems maybe important. So like who calls this? Set vertex buffers. Seems important. I don't know what this is supposed to do. So this goes like into our context. Maybe there's like a bound vertex buffer that's supposed to be set. Maybe. Been asking some people, how would you relearn C from scratch if you had to? Like data structures and algos, just do LeetCode stuff. I don't think I would do LeetCode personally, but I mean, if it works for you, it works for you. Just familiarizing with syntax and how stuff works. It's so hard for me to get myself in that mindset. Like, I've been programming for so long that syntax is like the lowest thing on my priority list. Like, you know, once you've learned a few languages, syntax becomes kind of like, it's all kind of similar. It's all kind of similar. I think I would, again, just try to make stuff. My answer is just always going to be just try to make stuff. And I think that by doing that, you'll have like motivation to push through whatever bullshit comes your way. But I mean, again, that's just for me. Whatever works for me may not be what works for you. But for me, just trying to do stuff means that I have to learn it by mistake. And that works well. Okay, can we see it? Who else calls set vertex buffers? Let's see other implementations of this thing. So, like in VerGL, they have like their context, and they do have a vertex buffer set up here. So it looks like we are probably supposed to hold that thing in our context. So let's try that. We'll be like, yo, give me a Sphero context. Which we can cast from a pipe context. Then in here, we'll say our vertex buffer. I don't know. We'll kind of like slap this here. And what does like take ownership mean? Take ownership would be like probably if we are in charge of freeing this thing later, would be my guess. That would be my guess. Let's look at the verGL implementation again. So do they use this at all? They do. So if they have take ownership, if it's not take ownership, then they resource reference. Okay. Set vertex buffers. Bind an array. Number of consecutive vertex buffers bind. Unbind slots after the bound slots. The caller holds buffer references, and they should be taken over by the callee. This means that drivers shouldn't increment reference counts. I see. But we should increment reference counts otherwise. So here we probably do something along the lines of like I is less than num buffers. We're gonna do like, what is this trailing slots shit? Unbind slots after the bound slots. What does that mean? Does that mean that I'm supposed to so num buffers, this is to bind, and then I assume that like this is plus unbind. And we're just not going to handle unbinding for now because I don't really give a shit. Let's just kind of like assert here that num buffers is equal to 1 for now. And then we'll say context vertex buffer is equal to vertex buffers. Probably dereferenced. Maybe this is like this. Okay. Then if we are not supposed to take ownership, then we need to increment the reference count. So here we look at ctx vertex buffer resource or something. Probably. So if not takes ownership and not is user buffer, probably. Then we do this, which takes in something and something else. So can we look at another usage of this thing? All right. What's the like other part of this? What is like the null parameter here? So the source and dest. Oh, dest equals source. This is wrong. Can we look at like the vergl side again? So this went into here and then into here and then into here. He did dest is source. Okay. I see. So we are supposed to resource reference like. Does he do something otherwise if he doesn't do that comparison? On reference the buffers. Copy over the other members of pipe vertex buffer. Oh, I see. So we copy the resource reference, and then the rest of the structure we copy after. I see. So it's kind of like this, right? Wait, where does he that like mem copy? Yeah, I don't really understand what like the destination thing is for. This just does a copy, which is fine. Oh, and then he just checks if you need to destroy the old thing. I guess is probably what's happening here. I guess? Is there like... Yeah, it must be. Alright. I don't know. We'll follow behavior. We'll follow behavior. So here we go to the output here from the input at vertex buffers 0. Okay. And now he's mad because this needs like buffer resource like this. All right. Fuck it. That seems reasonable, maybe. Maybe. Which means that then when we draw VBO, we're not supposed to be looking at this as much as we're supposed to be looking at the vertex buffer. So let's ditch this for a second and we'll just look at like our context. We have the user, we have the thing stashed. So we should just be able to like, look at like vertex buffer buffer resource. So here we have like our sphere resource. Yep. Yep, that looks right. We have our dummy resource. And then everything else there is just fine. Hold on. Hold on. It's like this. All right, let's see if that is like does something sane. If so, we kind of like understand what it's supposed to look like, at least a little bit. Now, we probably will still have to extract some information from the info in some way, shape, or form, but we'll get there. Okay, so that's good. That is really good. So here we are seeing our triangle on every frame, which is awesome. Very, very awesome for us. And now probably this info is going to tell us more about like how are we supposed to draw this shit? I don't know. Mode. Okay, so this is important, I guess. This tells us if we're drawing as triangles, lines, points, or whatever. If the draw is not indexed, how do we get like the minimum and maximum? Right? Like somebody is calling like draw rays from index 0 to 3. Where does that come from? We saw this was null. We saw this was null. So it has to come from here. Oh, it's probably draw ID offset and num draws, probably. Draw ID. Can we like GDB and check? Break at sphero drm winsys dot c line 364 should be good enough. Let's run and see. So this should be telling us the first and last vertex. The first and last value, I guess, that we want to draw. So if we look at like draw ID offset, the index of the vertice we should see. So I expect offset to be 0 here. Nice. And I expect num draws to be like 3 or something. 1. Okay. That's not what I expected. Not what I expected. Can we look at like the documentation for this? Will it tell us? Ah, nice, it will. We should just read. So for indirect multi-draws, num draws is 1 and indirect draw count is used instead. Okay, so then we should be looking at indirect caps. Always supported, direct multi-draws. Pipe cap multi-draw indirect multi-draws, indirect draw count. I don't know what an indirect draw is right now. Differences against GL multi-draw and GL multi-mode, info mode, and draws index bias are always constant due to the lack of hardware support for and CPU performance concerns. Only start and count vary. Okay. Direct multi-draws are also generated by U threaded context, which looks at head and galleon command buffers and merge single draws. Okay. So draw info, offset to add for draw ID param of each draw, array of start count pairs for direct draws. Okay. Indirect multi-draw. Indirect multi-draws. Okay, so it should be one of these. Should be one of these. So we should have like indirect, null, draws not null. Got it. Okay. So draws here has a start and count in the index bias, which I don't know what it means yet, so we won't handle it. That's the easy fix. So for unsigned, int I equals 0, I is less than num draws, plus I, we should look at the draw parameters. So start 0, count 3, index bias, big number. But 0 to 3 makes sense. We are drawing 3 vertices. 3 elements. right? One, like we're drawing a triangle, 1, 2, 3. Bam. So how do we know? How do we know that the data that we're looking at is is a 3D vertex, right? That's fed to us when we like run our test app. Uh, we are basically telling it with these parameters. We tell it that we have these are like the, how to treat one element, right? We're saying here that like we have 3 floats for an element. And if we had like, is that right? It must be because we do see the triangle. So can we? I want to read the documentation of GL draw arrays a little bit because I feel like I always get confused about whether or not we're looking at like individual floats, like size, number of indices to be rendered. I see. So they call this thing an index. Okay. So can we? I guess maybe the info seems like maybe where we should look. Info. Number of instances, start instance. Increment draw ID. Did we implement anything that tells us about like when does anything look like it looks like GL vertex arrays or something? Whatever the fuck that thing is called. Viewport state, rasterizer state, blend state, polygon. No, nothing here really looks like it, so it should be in here. Either maybe in set vertex buffers as well. We should double check this as well. So the vertex buffer has offset to the start of data buffer in bytes, but otherwise nothing really that interesting. It really feels like it should be in the info somewhere. Hand wavy, that's kind of how I'm feeling. So, can we just like print out the info? Okay, so we have like index size 0, view mask 0, primitive restart false, has user indices false, index bounds valid true, increment draw ID false. Nothing in here is like numbers though. I want like numbers. Nothing in here looks like what I want. Draws also not really looking what I want, like what I want. Can we look at like bind vertex elements state? No, vertex elements? This might be relevant. Source stride. Yeah, this looks promising. Where is this set? Create vertex element state. Yeah, you know what? This looks kind of interesting. For sure. Can we like breakpoint here? Okay, so I'm looking for breakpoint 2. Okay, backtrace here. Does he come from draw arrays? Okay. Can we look at like source stride 12? Source format 15. Okay, this looks like the relevant stuff here. So it looks like we probably have to say like struct sphero context is equal to a cast of the input. We here are going to like, I guess, just assign this. Is this like a reference counter thing? No. So I guess here we do like elements is equal to malloc. Is it calloc the one that does more than one? Yeah. So I want I want to do like num elements thing of size of struct pipe vertex element like this. Okay, this guy needs like a vertex elements here, as well as like an unsigned num vertex elements. Okay. 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 Yeah, and we mem copy the stuff over. So we go like mem copy from ctx or two vertex elements from input, and we want to do size of input times num elements is how much we're copying. Okay. And I guess really this is not where we should bind this thing, or we bind it here. So here we just return this. So this is where we actually do the binding. And it kind of seems like the thing we should return should contain the number as well. So we should do like sphero vertex elements. And he's just going to be like, oops, unsigned num elements. And then elements is going to be like a struct pipe vertex element star elements. I don't know. Seems reasonable to me for now. So we're going to be like struct sphero vertex element star is equal to like malloc size of vertex elements, sphero vertex elements. And if we wanted to get crazy, we could actually do one of those like, you could do one of like these, you know, where you kind of like inline a pointer that has variable length at the end of a struct. But I don't want to do that because that's work. So instead, we'll just do double pointers. That's fine. So it's like this. Hello, hello. So going. Good. How are you? So the elements here is just going to be the same thing here. We don't need our context at all. And then we just return elements. Okay. Then when we bind this thing, we're like, yo, I have some of these. Right? And then we just go, yo, context gets this from lms num elements. Vertex elements comes from lms elements. Okay. Did I spell this wrong? Sphero. There we go. So now when we do the drawing, we should know kind of like the format of these, right? So we're kind of hoping to see like, I don't know, something that's like num vertex elements equals 1. We're only supporting one thing for now. And then as we draw that thing, we like pass that in as the input to our shader when we draw it, right? So it's like something along the lines of like, this thing must have like something interesting in him, right? He has source format, source stride. Pipe format. Okay, let's look at that. Pipe format. enum pipe format. Here we go. So I'm assuming that this is like, geez Louise, man. Let's just try to look at it. Can we like get the names of these formats somehow? Can we look for like R64 uint? Maybe in all caps. Nope. All right. Unlucky. So let me think for a second. We are expecting the format of this thing to be like float. Right, so I'm expecting something along. Can we like look for float in this like giant list of shit? Like maybe R32 float? Maybe L32 float? I guess maybe GDB will tell us, huh? That's probably the way to go. So can we look at when we call draw VBO? We must have something interesting here. So let's just build, upload the latest and greatest, and take a little peek. Little peek under the hood. Okay. We want to break at one, probably. I think that's probably fine. In the draw VBO command, and we can just look at what we've stashed here by this point. So can we like print out like CTX vertex elements? Whoa. Where the fuck am I? Let's breakpoint at like Sphero DRM winsys.c line 389 or something. Del2, del1, continue. Okay. PCTX. Good. PCTX num vertex elements. PCTX vertex elements. Okay. Chilling. And what's in here? Source format 15. Right. I think we've looked at that already actually. So where was that like pipe form here? So we're at 16. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. What? Oh, 15? Hold on. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That makes more sense. So this thing means 3. This is like RGB is also like XYZ is basically what it's saying. So we're saying we have an input of 3 floating point numbers. Perfect. So here will be like CTX vertex elements source format is equal to pipe format R32G32B32 float. Right, that's what we said. 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Yes. Okay. So if this is true, then we can try to run our shader for the data here. We've said there's only one element. And we need to kind of package this stuff up by stride. So I guess, what is like the way to do this? I'm not sure. Let's look at our libgpu API. So eventually this is going to go over the wire to the GPU. The GPU is going to execute this stuff. He's going to be like, yo, here is the format for how I expect you to interpret the data. Which kind of makes me think that in libgpu, we need to like define, we need to have like some sort of like definition of the inputs. which makes me think, let's look at this for a second. So our shader runner, how do we run this thing again? We create a shader executor, and he is run with some inputs. Now, probably we want to run this thing on many inputs at once, right? So we probably want like shader inputs. We're gonna have some sort of like pointer here, right? We're going to have some inputs types. Let me think about this. Inputs. We're gonna have like an array of these things probably. Hand wavy. We're gonna be like my input has this stride and offset from the initial data. Okay. That seems reasonable. So then our shader inputs is just going to be like base pointer with an array of shader inputs. Right? That's kind of what I think we can expect. Maybe we just do this. So when we execute, maybe we execute with like a base pointer. And yeah. This seems right. Input base. Input defs. Okay. So then we need to say how many of these we're going to input. Okay, so I actually kind of want this to say the same, to be honest. We're going to call this execute 1. And execute is going to look a little crazier. For now, I'm going to say this is void. I don't know what this is going to return yet. We'll kind of figure that out. But this seems reasonable to me. Okay. So we're going to go for however many LMs we're trying to draw. Num indices, I think is what the terminology in OpenGL. We are going to basically try to interpret the data input data. So we're going to go like, we're going to have some sort of like variables. Yeah. So we're going to call this like the input defs. And we'll call this like run inputs. One LM inputs, we'll call it. This is going to have to be like an allocation of a variable, and we're going to have input defs len of them, right? So for each input, we're going to create a variable that we pass into our one loop of the shader. Now, how do we actually implement this? Who knows? Who knows? We're going to be like, for 0 to input, for input defs 0 onwards, we're going to have like def I. Okay. One LM inputs I is going to equal something. I don't know what yet. Presumably it's going to depend on the shader input. We're going to need like a type here too, huh? Okay. Yeah, that makes sense. So we're going to be like, depending on the type here, if it's like, I guess else, we'll panic for now. Unimplemented input parse. That means we only have to handle vec3, which is the only interesting one for us for now, right? If we have a vector 3, we're going to have to look at like, can we do like this? Base opt here. Let's see. For here, we'll do like const base, we go to base opt or else return. Whatever. There's nothing to draw if there's no data. Could probably go at the top, to be honest. We're gonna go like base plus def offset plus the stride times I. No. Plus the stride times I. This gets J. Yeah, so if we're at index 1, we move 1 stride over from the base. Cool. So this is going to be the like data pointer. Then we're going to look at this as a like multi-element float32 pointer. And we're going to just say we need to like put a block here so we can break block with a variable that says vec3 is equal to, oh yeah, we're getting there. Data pointer 0, 1, 2. Oh yeah, I think that's it. So now all we have to do is define the shader input for execute. So let's start here by running our unit tests, which are no longer going to work anymore because execute has, the API here has changed. So let's start here. So we're going to allocate a buffer. Right? And we're going to have like a bunch of floats in here, I guess. Right? And we're going to group them by 3s. Right? So we're going to go like 1.0, 2.0, 3.0, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Then what are we going to do? I guess let's think. We're going to call execute with a definition of these. So the definition is going to be like shader inputs so we're going to have like offset 0, stride is 12, right? 12 bytes because there's 3 floats in sequence that we care about, right? Then the type is going to be vec3. Okay? So now when we execute this thing, we should be able to execute it with like the base opt, which is going to be input buff pointer. Then we want the input definitions, right? Then we're going to want num indices, which is going to be 4. We have 4 groupings of 3. And now I guess we will, if we're going to try to test this thing, this should return some variables. And the output is going to just be one output per input. I guess makes sense, right? So we're going to say like outputs is going to be a alloc with num indices of variable. Then when we can just call execute one, with the 1lm inputs. Oh yeah, that looks wonderful. So now we should be able to say that our output's length should be 4. And we should see something along the lines of an array of these guys. And we just should be able to like do this. Right? Let's see if it compiles. Obviously not. It never does. So member function expected 3 arguments found 1. Can we just do like this for now? We'll get to this one in a second. And then 351, he's mad because this should be a compiled shader, so we need to do like load this or something. Sure, and then this thing needs like an allocator. Okay, he's mad because input buff is a problem. Fine. Then expected type shader input found const 1 shader input 362. Throw another const here, then he should be fine. Any opaque needs this to be like a pointer cast here. For that to work right. Pointer cast discards qualifier, so here we need to write const probably. Expected shader input found const at 369. All right, fine by me. Oopsies. Or else return. Here we should just be like error no inputs or something. I'm sure that's not correct, but it's good enough for now. This needs to write try here for indexing to work correctly. Boom, boom, boom. Here as well. Boom, boom, boom. Const any opaque and U32 cannot be added. Why not? Oh, does this have to be a multi-element pointer or something? Can we just do this as like a like this? Cannot expected type this found that. Can we do like a base opaque and then base? Can we do it like this? Is that allowed? That seems fine. And then here we just need this to be a pointer cast as well. Probably with an align cast as well. He's probably going to get mad here. Yep. Fine by me. Discards const qualifier. We will write a const here as well to get him to shut the fuck up. And then outputs I expected. Let's execute 1. I guess there could be more than one variable here, huh? I guess we'll do this. const one ret is equal to this. Stood debug assert one ret len is equal to 1. And then we can do outputs at 1 ret is equal to. There we go. This isn't right, but it's fine. It's good enough for now. Now he's mad that we don't return outputs. Fucking whiner. Because, like, theoretically, each shader could, like, output multiple variables. We're just, like, not handling that right now. We have a lot of leaks that are annoying. So can we, like, get the leaks out of the way first, and then we'll handle the rest? Defer. So this? Is that the only one? Is there more? Outputs.append, right? So we have to clear the outputs. And then here we need to do like get rid of this guy who has been allocated. Okay, is that fine? Okay, yeah. So we have we still have some more leaks here. So on 1 elem inputs, that's fair. All right, is that the last one? Please tell me that's the last one. Memory address leaked here at compiled shader load. Why? Oh. Shader data is equal to this. My bad. Defer shader alloc free shader data or something. All right, is that the last one? Please. I'm just trying to clean up the output just a little bit so I don't lose my mind. There we go. Okay, so this test now is no longer working. Can we like stood debug print the outputs? Let's see what we got. Okay. 123-258-369-470-71. It's weirdly not that wrong. It's like a little wrong. For sure. But let's start with the fact that this is supposed to be expect equal slices. So maybe the error will be a little bit more sane now. So we're saying that we have a type of variable. Okay. Now this is passing? Shouldn't it not be passing? Let's do... okay. So expected this output, instead found this. 1, 2, 3. Oh, did I just do it that way? I did. 2, 3, 4, 5, 6, 7, 8, 9, 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this is just right. Hell yeah, dude. Wait, that's sick. That's sick. So we have now run on a like chunk of input data with this like definition where we say here is how our inputs are formulated. And now we need to expose a C API that exposes this. So can we say that we like bound vertex data at some point we like we started working on like make GPU shader executor run on input buffer. Now we are on the the topic of expose C API to generate input definition. So like making this thing is not super straightforward. I think what we're gonna do is we're gonna be like struct libgpu shader input defs. Okay. We're going to make one of these. Libgpu shader create input defs like this. Then we're gonna add functions to push values. So we're gonna go like take in the shader input defs here. And we're gonna be like libgpu shader input defs push vec3. And we're gonna push in the offset and the stride. Okay. Then when we execute the shader, we can just pass in like data with datalen of the shader itself, along with the shader input definitions. And then what else do we need? We need like the buffer, right? The data buffer, as well as the number of elements. Right? Something like that? Okay. So pub export function libgpu create shader defs. This is going to return a shade, like some sort of like I don't know. Let's figure it out. I guess we want like shader input builder. That's kind of how I'm feeling this should live. Oh, we're in the wrong file here. Hold on. Right, so we have these like input definitions that we want somewhere. So before we do that though, we're gonna have to create them as we go. So we're gonna do something that's like maybe we just do like shader input builder is like an array list of shader input like this. And then here we're just gonna be like we have allocator is global GPA allocator, right? We go like shader input builder initialize with our allocator. But before we do that, we do like shader input builder, we allocate one of these. Right? Something like this. Yeah, that looks right. So now if we want to do whatever this shit says, we take in our builder, right? The offset as a U32, stride as a U32. And we go like builder append. We go like tip is equal to vec3, offs equal offs, stride equals stride. Boom. Simple, really, if you think about it. This needs to be like catch return false, return true, And we do a couple more. So compile shader is fine the way it is, but execute shader needs to be updated with some new APIs. So we added in datalen input defs is going to be a shader input builder pointer, which we did down there. Yep. We have the data buff. So this is gonna be the fuck libgpu.h. So the execute shader, this is gonna be the shaderlen, data buff, and numelement. So this is gonna be shader. Okay. Shaderlen. Input defs. Data. And num elements use size. Okay. So now when we execute this thing, it should be more like whatever the fuck we did in our unit test. Input buff pointer. So this is now just data. Shader inputs. We need like input defs items here. And num elements. Okay. This like might work. Yeah, that might work. So now that we have the C APIs that work here, assuming this builds, which it probably won't because I always fuck shit up. Right, we can't try at 546. That's true. Should just be a catch return null. Let's check it. Okay, good. Okay, so now we go back into the Mesa code. And instead of doing this, we should be able to be like, struct libgpu shader input defs is libgpu create defs like this, right? Then we go libgpu shader push input defs pushback 3 with the vertex elements 0 source offset and the source stride here. Boom. And then we also have to put inputs here. So now we have like an input definition. And now we should be able to call libgpu shader execute. Execute shader. With the shaderlen, which we don't have right now. But what else does this take? The rest we can probably do. Input defs, we should call this. Okay. And then what else goes in this? The buff and the num elements. So num elements comes from, I already forgot. Was it the draws? Yeah. So let's do assert num draws 1 for now. We'll have to fix that up later, but for now, we're okay with just cheating. So we can look at draws 0 count. We need to support start offsets, but we don't right now, which is fine. And then the data buffer is going to be like where does this come from again? The context? Vertex buffer? It's res, sorry. Res data. Boom. All right, that's looking pretty good. That's looking pretty good. Okay. So now we just have to get the shader state here. So we'll kind of store on our context, I think, a vertex shader or vertex shader length. What do we call it? We just called it VS shader. And we'll call like this. Okay, nice. Now, when we create our vertex shader, we need to return this like chunk of shit that we made. So can we go like struct sphero shader, sphero shader state, I guess we'll call it. He is just gonna have void star data size t len, right? Which means that now we can just return that. Boom. Kind of like this. Right? Except this thing has to be malloc, so malloc size of struct sphero shader state. There, like this. Boom, 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 boom. All right. And then these need to be arrows. Fine. That seems chill. And then when they bind the vertex shader state, here we get our like bullshit that we just made, which I'll just kind of put up here with like other types somewhere. Actually, where it was fine. So here we say that we have like a struct sphero context star context equal to a cast from the PC pipe context because it's the first element, so that's fine. We take the state as a sphero shader state. We'll call this state opaque, like this. Then we can be like context vs shader is equal to state data, and vs shader len is state len. Boom. Okay, which means that when we actually try to fucking call this thing on draw VBO, then we should have the vertex shader and the vertex shader length, and maybe everything just kind of fucking works, right? Maybe. I give it like a 50% chance. He doesn't like that libgpu execute shader doesn't exist anymore. He does. So what's he actually complaining about? It's right here. Yeah, I don't know what he's bitching about. Unknown type input shader defs. Ah. Because I need to write struct here. And here. That's a really good point. All right. We compile. Let's fucking go. And let's do our moment of truth here. No way. Okay, wait, hold on. So we're printing the commands here a lot. I don't really want to be doing that. I want to print the output. But the fact that we're not crashing is really good. Okay, so let's get this shit out of the way. And then, other than that though, we should be getting the output here. Oh, wait, no, wait, fuck, no, wait. Guys, look at this shit. Look at this shit. That's fucking working. This is right. -5, -5, 0, 1. -5, -5, 0, 1. 0, 5, 0, 1. Those are our fucking 4D vectors converted from the 3D vectors from our triangle input. Right? If I go into, oh my fucking god, dude. Hold on. So if I go into like main here, and we fucking change this shit. So we change this like, let's add some more, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, and like 1, 1, 1 or something, right? We fucking zig build and copy this shit and run it. I fucking bet that we now see. Oh wait, hold on. We have to change our GeoDraw elements to draw more than 3. So we now have 3, 4, 5, 6, 7. Right? We change this to draw 7. He's mad because it's still running. Oh, look at that, dude. 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 1, 1, 1. Oh, I can't believe it actually worked, dude. I was really expecting more pain on the way. That's fucking awesome. Okay. That's actually so huge. So we've kind of done like this and this. And now the next thing to do would be to like huck this stuff over to the GPU and make it run over there. Yeah, fuck it. Let's do it. Let's do it. Okay. So the last piece here is essentially we need like a kernel API to upload a vertex shader and run it. So like let's start on like the PCI device side. So we'll kind of start at like we need to get like an environment for developing QEMU because it's like a little very subtly different. So let's get in here. And we're going to add a command to upload a vertex shader as well as execute the shader. As well as upload data. You know what? I don't want to do that right now. I'm tired of shit. I can feel like my brain fog setting in. And I think that we just got like a really big win. And I think that it's likely that with the amount of stuff that we're going to have to do, that it will push over like 30 minutes. And I don't really want to go that long today. So I think we call it there on a big win. Like this is actually like so massive. We're so close, right? We're so close to like a vertex shader end-to-end working. So I'm happy with that win. That's very exciting. So what do? We figured out how like Mesa figured out is strong. We kind of like poked around the Mesa code base to the point where we could get vertex shaders or vertex data, I guess, accessible in the right spot. So they call this draw VBO command where we're supposed to actually do the drawing. We implemented buffer subdata as well as create element state and bind element state and set vertex buffers. I think we set all of these, right? Yeah, so the idea here was that we could figure out, like, OpenGL is informing us of the structure of the data as well as the data itself. We implemented the stashing of the vertex shader as well as execution of a shader with an arbitrary number of inputs, which is pretty big. We like stashed our like data in like Mesa land for now. Eventually that will have to be adjusted to be uploaded to the GPU. And then we run that stuff over here. Very cool. Very happy with that. So thank you for watching, guys. If you like what you saw, we stream most days at around 12:30 Pacific time to 4 o'clock Pacific time. It is 3:40 Pacific time now, so anywhere between 3 and a bit hours ago to now is when you should expect to see me live. 12:30 to 2, we typically work on like kind of like supplemental content, I like to call it. So stuff that does not really impact the main project visibly, but might make things easier behind the scenes. So today, for example, we were working on making the GPU API asynchronous, right? It's not something that's really worth, I think, covering on the mainstream, but is worth doing. So happy hour, 12:30 to 2 is stuff like that. And then 2 to 4 is the stuff you see here. So if you want to see more of that, the 2 to 4 segment is archived on YouTube, and the 12:30 to 2 segment is archived on YouTube under the members section or on Patreon. So if you want to see us work through extra content, feel free to throw some money at it. Otherwise, no big dealio. Thank you for watching, and I'll catch you on the next one. Goodbye, YouTube, and Twitch. Let's find someone to raid.